In this video, we discuss Bitonic sort in CUDA. First, we discuss what a Bitonic sequence is. A sequence A sub 0, A1, blah, blah, AN minus 1 is bitonic if the sequence first monotonically increases and then monotonically decreases. Okay. So that means for some k, we have A sub 0 smaller than or equal to A1, blah, blah, smaller than or equal to AK. Okay. So this is monotonically increases. Okay. And then AK is larger than or equal to AK plus 1, larger than or equal to blah, blah, larger than or equal to AN minus 1. So this is monotonically decreases. So for example, this sequence is a Bitonic sequence because the numbers first increases. Okay, so we have 8, 10, 14, 20, 30, 45, increases up to 45, and then the sequence decreases. Okay, 40, 36, 28, 15, 2. Okay, so this is a Bitonic sequence. So basically, a Bitonic sequence consists of two segments. One segment has the elements sorted in ascending order. Okay. The other segment has elements sorted in descending order. Okay. Or the descending and ascending can be reversed. So that means the sequence could first monotonically decreases and then monotonically increases. So for example, this is also a Bitonic sequence because it first decreases, okay, 9, 8, 3, 2, and then increases 4, 6, 7. Okay. So in short, the Bitonic sequence has two sorted subsequences or two sorted segments. Okay. Now we discuss Bitonic sort. Consider a sequence A0, A1, blah, blah, AN minus 1 with n equals 2 to the m. So that means the number of elements in this sequence is a power of 2. So in Bitonic sort, we sort the first two elements A0, A1 in ascending order and A2, A3, the next two elements in descending order. And the next two will be sorted in ascending order again. Okay. So we concatenate them, the sorted elements, to form a 4-element Bitonic sequence. Okay. Because after sorting, the two elements, two pairs are sorted. Okay. So when you join them together, it becomes a Bitonic sequence, okay, with 4 elements. And we take two 4-element Bitonic sequences, and now we sort one segment in ascending order and the other in descending order. Okay. And we repeat this process, then we get a sorted sequence. Okay. To illustrate this method, let's consider a simple example. Okay. Suppose we want to sort this sequence. Okay. 3, 7, 4, 8, 6, 2, 1, 5. So we have totally 8 elements, which is a power of 2. And we start with segment length equals 2. Okay. So we sort 2 elements at the beginning. Okay. And now we use this symbol, okay, to denote sorting in ascending order. Okay. So if you have two elements A, B, we sort them, then the minimum element will be on top and the maximum will be at the bottom. So basically, the arrow we point to the bigger element. Okay. And this symbol to denote sorting in descending order. Okay. So that means maximum at the top, minimum at the bottom. So again, the arrow points to the bigger element. Okay. So we arrange this sequence, okay, in the vertical form. So it's 3, 7, 4, 8, 6, 2, 1, 5. So we sort these two elements in ascending order, and this in descending order, ascending order, descending order. Okay. And so in step 1, we have only one stage. We sort this. When we sort this, we get say 3, 7, right? Ascending order. When we sort 4, 8 in descending order, we get 8, 4. Okay. 6, 2 in ascending order, we get 2, 6. 1, 5 in descending order, we get 5, 1. Okay. So these are sorted. So we concatenate them to form a Bitonic sequence 3, 7, 8, 4. Okay. And this also form a Bitonic sequence. Okay. And now we sort these two Bitonic sequences. This is in ascending order. Okay. And this is in descending order. Okay. And so that means when we sort 3, 8 in ascending order, we get 3, 8. Okay. 7, 4. So in ascending order, we get 4, 7. Okay. And 2, 5. Okay. In descending order, so we get 5, 2. Okay. 6, 1. In descending order, we get 6, 1. Okay. Remember, the arrow points to the larger element. Okay. So we repeat this process. Now we have to sort this again. Okay. But say the distance is halved. So here the distance is say 2. Okay. Distance between the sorted elements. Okay. So half them. Okay. Becomes 2. So we sort 3 and 4 in ascending order. Okay. So that is 3, 4. And sort 8, 7 in ascending order. So it becomes 7, 8. Okay. 5, 6 in descending order. So it becomes 6, 5. 2, 1 in descending order. So it becomes 2, 1. Okay. So in step 2, it consists of 2 stages. Okay. So we first sort this, okay, with distance 2, and then we have that, okay, becomes 1. Okay. And now we combine this, okay, to form this one sequence. Which, now this segment has 8, okay, elements. Okay. So at the beginning, this segment only has 2 elements, okay, and then your length, the segment length becomes 4, and now it becomes 8. Okay, so this is the stage 3. Okay, and we sort all this in ascending order. After this sort, we will have a sorted sequence. Okay, so 3, 6. Okay, we get 3, 6, 4, 5. So we get 4, 5, 7, 2. So we get 2, 7 in ascending order. 8, 1. So we get 1, 8 in ascending order. Okay, and then now we go to stage 2. Okay, so in like this. Okay, so the distance between the sorted elements becomes 2. Okay, so the distance between 2 sorted elements here is 4. Okay, so we halved to 2. Okay, so here 3, 2 we sort in ascending order, so it becomes 2, 3. Okay, 4, 1 is sorted in ascending order, becomes 1, 4. 6, 7, sorted in ascending order, so you get 6, 7, and 5, 8. It becomes 5, 8. Okay, so now the segment length is halved again, becomes 2. So 2, 1, we sort it, becomes, all these are sorted in ascending order. So it becomes 1, 2, 3, 4 becomes 3, 4, 6, 5 becomes 5, 6, 7, 8 becomes 7, 8. So we get a sorted sequence. Okay. So this example illustrates how it works. Okay. And now you might have seen that for every segment, the number of inputs is in the format of 2 to m. Okay. So it is 2, 4, or 8 in this example. Now this is a C implementation of this Bitonic sort. It's pretty straightforward. Okay. Now, so this is the Bitonic sort. Okay. So we sort the numbers. Okay. So the length here is the length of the segments. Okay. The length should be smaller than or equal to n. N should be a power 2. Okay. And we double the length, okay, until the virtuous length. Okay. So you can see that here the length is 2, the length of segment, okay, at this step. And in this step, the length is 4, okay. And the final step, okay, the length is 8, okay. Then after finishing this step, we're done. So that's what this means. So you have 2, 4, 8. Okay, each time we double it. Okay, and then for each length, okay, we have to go for different stages. Okay, so for this length equals 2, we just have one state, as you can see. Okay, we have to start. Okay. From 0 to start smaller than n, and we increment start by the length of the segment. Okay. The start is the starting position of the first element. Okay. We compare the 2 elements. Okay. And so for this element, say start equals 0, right? And then we increment the length by 2. Then the start for this comparison, so start equals say 2, okay, and then 4, and then 6, okay. For that's what this does. What this does, okay. And for each of these, okay, as we mentioned, we have different steps, different length. For length equals 2, we just basically go for this inner loop once. We sort it, just do the sort once, because so in this loop we have the distance equals length over 2. Okay, the distance here is 1. Okay, length over 2. Okay, 1, and we do this when distance is larger than 0. But next time, when we go back, okay, to this loop, distance divided by 2, okay, 1 divided by 2 will give us 0, integer division. Okay, so we just sort this once. Okay, but when length equals say 4, okay, we do this twice. Okay, and the distance is shortened by each iteration. So here the distance is equals to 2. Okay, we do it once. Okay. And then half the distance to 1, so we do it again. Okay, we do it twice. Okay, and here we have to do it 3 times. Okay, so that's what this for loop does. Okay, and each time we sort the 2 elements. So the elements are in the array A. Okay, we have to pass in the start. Okay, the length of the segment. and the distance, okay, that's the partner's position, okay. And then the sorted elements could be sorted in ascending and descending order, and this is determined by your starting position. We do this alternately. Say ascending is start divided by length, mode 2. If this is 0, okay, then it is ascending. Right? Start is 0, okay. Then we have this in ascending order, okay. And when start equals 2, when start divided by the length, 2, start is 2, 2 divided by 2, and you get 1, okay. So mode 2 is not 0, so it becomes descending, okay. So this ascending, descending, ascending, descending. The same for this, okay. Okay. So for this, okay, it is both ascending, okay. When start by the length, okay. For this 2, this and this, okay, they are 0, okay. And for this and this, okay, they are not 0. So this in ascending order, descending order, okay. So that's what this does. So this variable will determine whether we sort the two elements, okay, in ascending order or descending order. So we pass into this sort routine, okay. So we go through the sequence, okay. So from start to I smaller than start plus length minus distance I plus plus, okay. So for this case, we just need to do it once, okay, to sort, okay, because after we increment I, okay, then start plus length minus distance, okay, distance is 1, length is 2, okay, then and start 0, okay, then after increment data is no longer smaller than 1, okay, exit. And for this case, you have to do it twice, okay. So, and here, if the pair, okay, is out of order, if it is, we want to sort it in ascending order, and if AI, okay, is larger than the partner AI plus the distance, okay, then we make a swap, okay. Or the other case is that we need to do it in descending order, okay, and again AI is smaller than AI plus distance of order, we also do the swap, okay. So that's what this program does now. Let's copy this maybe later. This is a pin routine, nothing special. If the n number of elements to be sorted is smaller than 16, smaller than equal to 16, then we print all the elements. Otherwise, we print every n divided by 16 elements. Okay. We use a random number generator to generate some random numbers. Okay, and mode 900, so that the numbers are between 0 and 900. Okay. And if n is more than equal to 16, we print out the sequence before sorting also. Okay. And then we need to ensure that n is a power 2. Okay, so this statement n and n minus 1 not equal to 0. Okay, we will ensure that it must be 2. If not, okay, power 2. If not, then we exit. Okay, now this is because say n. If it is a power 2, then the binary number would be like 1 0 0 0 0 0, something like this. Okay, and then n minus 1 would be something like 0 1 1 1, all ones. Okay, so when n of them you get 0. For other situations it won't be 0. Okay, so that's one way to ensure n is a power of 2 for Bitonic sort. Then we call this routine, pass in the random numbers, okay, to do the sort. Okay. And then after the sort, we print it out, okay, and free the array. Now let's copy this and try this program. Let's copy this. So we call this bt sort cp, and we paste this. Okay, save it. So we get this one. Okay. Okay, so now let's compile this one. So we have nothing here. So that's what we just saved. So it's g plus bt sort minus o bt sort. Okay, so we compile it, and you can see that, that this is the random sequence at the beginning, and this is the sorted one. Okay, so you see that they are sorted. I can try a few. Okay, so it's always sorted. Okay, and so there's the C implementation, and the time complexity of this sorting algorithm, okay, could be calculated like this. Okay, briefly. Okay, for sorting random numbers, to use the Bitonic sort, okay, we need to form a sorted sequence of length n from two sorted sequences of length n over 2, like this. Okay. So to get this sequence, we need to obtain this sorted sequence and this sorted sequence. Okay, basically it is like that. Okay. From this and this. Okay, two sorted sequences, and we have to go through 3 stages. Okay, and we need, in general, we need log n stages. So briefly, the time to do the calculation Tn, okay, is basically log n plus Tn over 2. Okay, and if you solve this equation, so you can tell that the time complexity of this algorithm is big O n log n square. Okay, so this is not good, not very good compared to other popular sorts like heap sort. Okay, so the time complexity for sorting random numbers, okay, is theta n log n, and for quick sort is also a theta n log n, merge sort theta n log n, but this is not n squared. Okay, so in general, okay, if in a serial computer, so this is not efficient. But there are the nice thing of this sort is that, okay, the pairs of elements could be sorted in parallel, okay, and one thread can sort a pair, so we can have n over 2 threads working simultaneously. Okay, so in this example, we have one thread to sort this pair, another thread to sort this pair, another thread to sort this pair, another thread to sort this pair. So all these threads could work simultaneously. Okay, the same for this. Okay, 4 threads to sort this or 4. Okay. And actually, one can build a parallel network, okay, to do this sort efficiently, okay, as shown in this diagram, okay, where we interconnect these elements, okay, and there will be log n stages. Okay. So this becomes efficient. Okay. So let's see how we do this in CUDA. Okay. In CUDA, we can do things in parallel. Okay. So first, we just use one thread. Okay. So now let's first copy this. We copy this bt sort cpp to bt sort maybe to cu. Okay. So this becomes bt sort dot cu. Okay. And now all we need to change, okay, is to implement this swap function, okay, as a device function, so that it can be called by a kernel function in CUDA. Okay, so so we copy this. So we copy this and paste this. And this becomes the address. The address, and this will be global CUDA kernel. COBAL. Save this. And then, as before, okay, we need to declare the device memory. Okay. So we do this, okay, and copy the data, okay, to the device memory. So we can do that at the beginning here. So we save this. And so we just need to add this. And we use one thread only. So this will be 1, 1. Okay. And we could add this statement to synchronize the devices. and this should be DA, the device memory. Okay, the DA here. And after that, we copy the data back to the host memory and free the device memory. Okay. Okay, so others should be the same. We don't need to make any other changes. Yeah. And now let's compile this. MVCC BT short CO -O, and we can call this CO. Well, you can overwrite that one. Okay. So BT short. Okay. And again, you can see that the algorithm works. Okay, with one thread. Okay. And of course, that's not what we want. We want many threads to work together in parallel. Okay, so this is the multi-thread CUDA implementation. Okay. And we discussed before that, say in CUDA, threads are organized into blocks, and blocks are organized into grids. A grid contains a number of blocks, and a block contains a number of threads. Okay, and each thread has an ID, and the ID could be calculated using this formula. Okay, so it's thread.x plus block dimension.x plus times block idx.x. Okay, and we need to make so this I is the thread ID. Okay, this each I corresponds to a thread. Okay, and each thread will work on a sorting. Okay. And we need to ensure that I, the thread ID, is within the range start and I smaller than start plus length minus distance. So basically here, to ensure that it is within this range, the range that we want. Okay. So that's the thread that we need. Okay. So with this, all the threads could work in parallel at the same time. Okay. We get rid of the for loop here. So this is working in sequence. Okay. So now with CUDA implementation, we don't have that for loop. Okay. So all the threads would work in parallel. Okay. So all others are the same. The code won't change. Okay. And we need to define the number of threads in the block. Okay. We divide that to be 256. Okay. And the number of blocks, okay, is equal to the Sine function of n divided by n threads. We take the float here because we want to avoid integer division. Okay. And then the argument here becomes n blocks, n threads. Okay. Others are the same. Okay. Now let's make this change. Okay. So suppose we call this BT short. The BT short MT means multi-thread. So BT short empty. So we get rid of this and we just need this. Look better. Okay. And so we define number of threads and blocks. Maybe here. And here, okay, we just change this to end blocks and threads. And threads. Okay, so no change for others. Okay. And now let's compile this. So mv cc bt sort empty bt sort empty. Okay. So again, this works. Okay, so the numbers are sorted. Okay. Okay. Okay, so that's how to use multi-threads to do the implementation. Okay. Now finally, let's consider bigger N to compare one thread with many threads. Okay. Suppose we, what about this? Oh. Multiply this by 1024. Okay. And we compile this. So it still works. Okay. And now we do the same thing to the other one. Single thread. Uh, 1024. And compile this. MVCC BT sort.cu. Okay, so this one works also. And now let's compare their time. For this say single thread. Okay, so the time to execute the sorting routines, the tutorial is say 557 milliseconds. Okay, totally with that many cores. And now let's compare it with this one, nvpro.bt.mt multithread. And now you can see that, okay, the time for this one is only 116. Okay, so it's about a factor of 5 improvement. Okay, and so this is the advantage of the parallel computing, okay, or the advantage of the Bitonic sort, okay, when it's done in parallel. Okay. Well, that's what we want to discuss today. Okay. So if you think that this video is helpful to you, so please give a like. Thank you, and see you next time.